All right, so the very first thing we are going to talk about in our Math 116 experience is we're going to talk about exponential functions. And so what we're going to do is we're going to start by taking a look at some functions that I think we are familiar with and plugging in some numbers and just getting those brains working again with what it means to like plot some points and draw some graphs, because we're going to be doing a lot of that this semester. Okay, and so let's take a look at this, what we know. All right, I'd like to start pretty much every lesson we do with something that we know. I think that it's so important to say, okay, these are skills that I feel comfortable with, and building from there is entirely different than feeling like you don't know what's going on at all. Okay, so we're going to start with this function f of x equals 2x. And we're going to go ahead and pick some x values. So let's say -2, -1, 0, 1, and 2. And in general, I really like to choose sort of a center point, which is sometimes 0 and sometimes not, and then some positive numbers and some negative numbers. And so if we do some quick arithmetic here, if I take -2 and I plug this into my function 2x, what do I get?
-4.
Exactly. So we're going to end up with -4. What happens if I plug in -1?
-2.
What happens if I plug in 0?
0.
And this will be a +2 and a +4. Right? Now, this should be something familiar from, any one of the number of math classes that you've taken before this. But if we were to plot these points, right, if we were to plot this point -2, -4, we would go to our graph and we would say we're going to go to the left 2, right? So I would start here, I would go to -2, and then I would go all the way down to -4, right? And so let's plot that first point at -2, -4. And we can go ahead and plot the other points, -1, -2, 0, 0, 1, 2, and 2, 4. All right. Now, because we do have these pre-made grids here, we want to make sure that we're just counting the appropriate number of boxes, right? So the scale here, this is 2, so then half of that is going to be 1. And now if we go ahead and connect all of these, we see that we have something kind of like this, right? What kind of function would we call this particular
Linear.
equals 2x? Exactly, yeah, this is a linear function.
Oh,
right?
Yeah.
And so right down here, I want us to go ahead and just write for ourselves that this is a linear function. All right. And one question I have one question I have for you is, how could I tell from the table that I'm going to end up with a linear function?
To put it simply, you can tell because it goes in a straight line.
It does go in a straight line, but how would I know that from these y values that I have in my table?
The increments are all the same.
Exactly. And so when you say increments, let's see, how do we get from -4 to -2? Well, we add 2. How do we get from -2 to 0? We add 2, and we can see that for each one of these y values, if we just add 2 to the previous one, we're going to end up with, okay, there we go. We're going to end up with the same number, or that spacing is going to be equal. Exactly. Okay. And so that +2, +2, +2, that helps us know that this is going to be a linear function. Okay. So we could say that there is equal spacing between the y values. right? There's equal spacing between the y values. And I want to say my internet is being weirdly slow right now. So I know that it's taking a little bit of a lag for things to show up. My apologies for that. There's nothing I can do, but we'll just kind of go with it today. All right, so this is something that should be familiar to us, right? We have this function. We know we can pick some x values, plug them into the function, plot these points, and then see a picture, right? But what I want to take a look at now is maybe a different kind of function, all right? And in particular, let's take a look at a function. Maybe we'll name this one g of x. And just for the sake of quote unquote nice numbers, let's say that g of x is going to equal 2 to the power of x. So notice that we still have a 2 and we still have an x, but the location of them is different, right? And so if we're going to make a table, we could go ahead and say this is going to be our x values. And maybe for the sake of this particular question, we use the same x values that we used before. So -2, -1, 0, 1, and 2. And so if we were to think about what our g of x gives us, right? Let's actually start with 0 this time. Sorry, the lag is kind of annoying. So let's start with the 0 this time, okay? In other words, if we put 0 into 2 to the x, that's going to give us 2 to the 0 power, right? This is unsimplified intentionally. But Dallas is right. If we take 2 to the 0 and we simplify it, we should get 1. All right, so in the box below 2 to the 0, let's go ahead and write 1. All right, what happens if we take 1 and we plug it into the function? Well, we would get, 2 to the first power. And if we simplify that, that will give us 2. What happens if we plug in 2, like an x value of 2?
4.
We would get 4, and we got that because it's 2 squared, right? Now, I know you guys know what 2 to the first power is, 2 to the second power is, right? I know that we don't necessarily need review on that part, but I think sometimes things get a little trickier when we have negative numbers, right? So if I follow this idea of I'm just going to plug in the x value, then when I plug in -1, I'll get 2 to the -1. And when I plug in -2, I'll get 2 to the -2. What do those simplify to be? Yeah, I see those in the chat right there. That's 1/2 and 1/4. And those would be absolutely correct. And in the past, I've definitely had folks who think that 2 to the power of -1 would equal like -2 or something like that, right? That's like an easy mistake to make as you're thinking through things. But this is one thing that we're going to use a lot over the entire year. So I really want us to be considerate about like what it means to have a negative exponent. We can just write this as 1/2 to the first power, right? That idea of negative exponents, it's the same thing as moving that term to the other side of the fraction line. So we do indeed have 1/2 here. And if we do the same thing for the second one, we get 1/2 squared, or that's going to give us 1/4. Okay. All right, let's go ahead and plot those points here. So if we plot these points, we're going to get 0, 1. We have 1, 2. We have 2, 4. Right, those are the 3 points on the right-hand side. And if we plot the other ones at 1, we'll get 1, or -1, we'll get 1/2. And at -2, I'm going to get 1/4. And so I think we can already tell that we cannot connect these 5 points in a straight line, right? It's not a linear function, but rather we have a situation that is a little bit of a curve, right? And so if we connect all these points, we should end up with a function that looks something like this, right? Now this shape that we have right here, my friends, is called an exponential function. So with this exponential function, we're not adding the same number every time, right? We don't just do add 2, add 2, add 2, but how do we get from one y value to the other y value? Like, how do I get from 1 to 2 and from 2 to 4?
Are they squared each time?
I agree that 2 squared is 4, but 1 squared is not 4, or 1 squared is not 2. So let's find a pattern. Like, how do we get from 2 to 4? I agree that that's going to be times or raised to the power of 2, but how do we figure out the same pattern that works between any two of these points? Like, let's take a look at this one. How do I get from 1/2 to 1?
Would it be multiplying by 2 every increment?
Yeah. All right. So if we zoom in here a little bit, if I have a quarter, right, 1/4, and I double it, so times 2, I'll get 1/2, right? If I have 1/4 and then I have 2 of them, I end up with a half of a dollar. If I have a half and I times 2, I end up with a full amount. If I have 1 and I times 2, I get to 2. If I have 2 times 2, I end up with 4. Okay. So one of the things we want to be really careful about as we're looking for patterns is we don't want it to just work for one case. We want it to work for the entire function. Okay. So it turns out that just like a linear function means equal spacing between y values, an exponential function means that we are multiplying by the same amount between y values. Okay. So we are multiplying by the same amount between y values. So we're not adding the same amount, but we're multiplying the same amount. Okay. So I know that there's been a little bit of a lag, but let me see if I can get this all on one page for us, right? So for those of us who are not able to print these out, in case there's anything that you miss, you can take a quick look right here. All right, so what we're going to do next is we're going to talk a little bit more about this exponential function, right? And so this exponential function is really the centerpiece of section 4.1 in your textbook, all right? So let's take a look. All right, while this is syncing, don't know why this is so very slow. All right, so exponential functions. This is something that you'll find in section 4.1 in your textbook, right? And what we'll find is that this equation, f of x equals ab to the x, is going to be very much a function that we want to know what the different letters stand for. Okay, and we're actually going to be focusing a lot on the idea of word problems. And before that, like, freaks other folks out about like, oh, we're going to do word problems on the first day of class. I think that exponential word problems are actually some of the most straightforward ones that we can take a look at. Okay, and so we're going to take a look at this equation right here, f of x equals ab to the x, and let's just think about what each piece here is going to relate to in a word problem. okay? And so let's start with this letter A. Okay, so this letter A, what does this stand for? That, my friends, is going to stand for an initial value, okay? We might also think about this as the y-intercept. All right, so as we're taking a look at the equations, if we see a number for 1, we want to think, oh, that is the initial value, or that is the y-intercept, okay? The B number, okay? This B is going to be something that we refer to as a growth or decay constant. All right, a growth or decay constant. So when you hear that word, growth constant or decay constant, you're thinking about that number that is in the place where the B is at. All right, let's talk about this X up here. All right, this X value, when we get to word problems or even when we see it in an equation, what we want to think about is that that X value refers to a time cycle. Okay. And the last thing that we want to think about is what's happening on the left-hand side, which is our f of x. All right. And so in a word problem, what is that going to tell us? Well, it turns out that this f of x is going to tell us about our ending value. So it's not the initial value like A, but it's an ending value. But sometimes we think about that also as a desired value. Okay. Now, I know in a lot of textbooks, they sort of list what each of the variables means underneath. I like to do the color coding piece where I can see exactly like right on the equation what it stands for. That's a technique that I find helpful for me. But if that's not your jam, then that's totally fine. You don't have to color code. There's absolutely no pressure to do that. Okay. But knowing these 4 things, let's talk about what the graphs look like and then also look a little bit at some notation, because I think it's important that we know how to read different notations as they come up, okay? And what we're really doing here is building like a really good toolkit for the rest of the year, all right? All right, so we sort of have exponential functions in 2 categories. We have exponential growth that we see on the left-hand side, and then we have exponential decay, all right? Now, it turns out that when we're looking at exponential growth, that's a situation where, just like our 2 to the x, we sort of start flat, and then the function starts to go up pretty quickly, okay? So something like this, a picture like this, would be considered exponential growth. All right. On the flip side, all right, literally on the flip side, if we think about exponential decay, that's going to be a situation where we start pretty high up, and I'll wait for that to pop up on the screen. All right, so we're going to start somewhere up there. But then as time goes on, the function starts to lose, value. At first, sort of quickly, and then it starts to flatten out a little bit more. Okay. And so our exponential growth and our exponential decay both have that same shape, except one is going up and the other one's going down. Okay. Now, one thing that would be important for us to know is that both of these graphs share a few features, okay? And if we go back and use the same colors that we had from the equation, this point right here with the purple, we could say has a coordinate of 0, comma a. Right? That's actually going to be the same on the decay function. That y-intercept is going to be 0, comma a. Right? So same on both graphs. 0, comma a is going to be that y-intercept. There is also one more shared feature between these two. There we go. There's that other 0, comma a showing up. There we go. Okay. Both graphs also have something that looks like this. Anybody know what that's called?
Is that like the
X-axis.
X line? Yeah, x-axis.
It is the x-axis, and it happens to be in the same place as the green line right now. Anybody ever
It's
heard?
the asymptote, right?
Yeah, there's actually, we're going to go ahead and call this a horizontal asymptote, right? This green line is called a horizontal asymptote. All right. So the green line is a horizontal asymptote. Now, what does that mean? For our contexts right now, what I want us to think about is that it sort of tells us where the end of the graph is headed. Okay, meaning that this end of the graph sort of flattens out and it's going to get closer and closer to that green line. In our exponential growth, like this end, the left end sort of flattens out and gets really, really close to that green line. Okay. And we'll dive more deeply into what it means to be an asymptote, but I do want us to write the equation for that. So we could call this the x-axis, but does anyone know an equation that we could write for this horizontal asymptote?
Isn't it like x equals everything greater than? I'm just spitballing. I feel like
You're fine. So every point on this line, right? Every point on this line, do all those points share the same x values or the same y values?
The same y value. Would it be y equals 0?
Yeah, every single point on this green line shares the same y value, right? Every single point has y equals 0. And so collectively, we can just say that the equation here is y equals 0, okay? Now, I think a lot of folks try and memorize. They're like, is it x equals? Is it y equals? And sometimes we memorize wrong, right? And so we want to think about like why that is. So if all of these points have the same y value, then it should be y equals whatever those values are, right? And so this one also on the exponential decay will have the same equation, y equals 0. All right. Now you might be sitting here looking at these two graphs and saying, well, if these are all the things that are the same about them, how in the world would we even be able to tell how they're different based on the equation? And it turns out that the orange B, our growth or decay constant, that is the thing that tells us whether our graph is going to look like the growth function or whether it's going to look like the decay function. Okay. Here's how we tell. If we look in our equation and we see that our B value is greater than 1. Okay, so you scan through your equation, you look at that number in the orange and you say, oh, that number is bigger than 1, then your graph will look like this. It will be an exponential growth, guaranteed. Okay. Now, if you look at the b value and it turns out that the b is between 0 and 1, then you're going to have a case of exponential decay. All right, so literally the b value is where it's all at. That tells you, are you going to have an exponential growth or are you going to have an exponential decay? All right. All right. We're going to finish off this part of the conversation talking about some things that I think traditionally are hated by students. I don't know why, but are incredibly important, again, in sort of setting ourselves up for success for this year, okay? And that is domain and range. So when you hear the word domain, what are some other keywords that pop into your brain?
The average?
It is not an average. So the domain, if we look in the chat, it looks like someone has said that it's all possible x values, okay? And so our domain, what we want to think about here is which x values can we input? Right? So when we think about domain, we want to think which x values can we put into our function, all right? Are there any that we cannot put into the function? Like if we put that number into the function, something weird is going to happen. Like we'll have like a negative number or like something that we don't want out, okay? Domain often gets paired with the word range because we just changed one thing about this. Instead of saying which x values can we input, we're going to say which y values can come out of the function. Right. And so a lot of folks, when they're thinking about domain and range, are thinking domain is like x values, range is like y values. Okay. Now, I find it kind of helpful if I have a graph to help me answer questions about domain and range. Okay. I am also a very visual learner. Right. So some of us in here might be sitting here and being like, oh yeah, I'm a visual learner as well. And others of us are like, I don't know, pictures don't really make that much sense to me, but it is going to be a part of our mathematical development that we're going to embrace this year. Okay. So if I look at this exponential growth function, right? If I look at this exponential growth function, I sort of think about it in 3 categories. Are there x values that are positive? Like all of these x values are on this side. Those are all positive y value or positive x values, right? So maybe another natural question would be to ask ourselves, are there any negative x values here? And maybe we would say, yeah, there's all of these. These are negative x values, right? And then sort of the special case that I like to think about is, can I plug in 0? Like if I take 0 and I plug it into my function, is that going to be okay? Or did I just ruin the entire world, right? Positive x values work, negative x values work, and 0 works. So what we're going to say for our domain is that we are saying that all x values can be put into the function. All right. In words, that is literally what we're saying. All x values can be put into the function. How do we write that in notation? Okay, that's sort of the next question. How do we write what the sentence in the blue in mathematical notation? There are two ways that I want us to think about, okay? One way to say this is that you're going to go from negative infinity there we go, from negative infinity all the way to positive infinity. All of those would be x values that you can put into the function. But we're going to surround these with parentheses. Okay, so we'll put parentheses around that negative infinity to infinity. This first thing that I wrote right here is something called interval notation. Okay, interval notation. We're going to be using that a lot because a lot of textbooks and instructors use that format. So I want us to feel comfortable not only writing it, but also reading it, right? When we see this, we want to know what it means. Anybody know another way to say from negative infinity to positive infinity?
Could you do negative infinity is less than or equal to x, which is less than or equal to infinity?
You could do that as well. Yeah, like if you had negative infinity is less than x, that would be okay as well, right? Anybody here ever heard of the phrase all real numbers?
Dang it, I was just about to say that.
Perfect. I think it's one of those phrases like sometimes when we're panicked and we're like, I don't know the answer, all real numbers, it must be, but it is in this case actually true, okay? So another way that we could write this is we could say all real numbers. And the way that we write all real numbers, if you look in a textbook, it's like a uppercase script R, right? I don't have like textbook sort of handwriting. So my shortcut is I'll write an R with a double like vertical line. Okay. So I'll write that one more time. I just write like a regular R, right? A regular uppercase R. And then I just add a second line, second vertical line. That's what a lot of mathematicians do when they're trying to write like script. They'll just make that second line. Okay. So this scripty uppercase R, this stands for all real numbers and means the same thing as from negative infinity to positive infinity. Okay, those are going to be primarily the two notations that we use in class. We'll use interval notation a lot. And as we need, we can use this capital R to say all real numbers. All right. All right, so let's answer the second question about range, all right? So range is like which y values can come out of the function. And I like to group them the same way. Are there positive y values on either of these graphs? Do we see positive y values here?
Yes.
Yeah, we do, right? In fact, everything that we see here, I'm gonna have to figure out this internet situation before Wednesday. But everything that we see in that red, all of that's positive, right? Can we get a y value of 0?
No.
That is correct. We cannot get a y value of 0 because in fact, this part right down here, it's going to get closer and closer and closer, but it's not actually going to get to 0. Okay. Last part to this question, can we get negative y values out?
Not with the current graph.
Right? We don't have any picture down here at all. That would be where the negative y values are. Since we don't have any of those pictures, any of the graph there, we would say that our y values that can come out of the function, we could say that is going to be all positive y values can come out of the function. All right, so this phrase in the purple, all positive y values can come out of the function, that is what we want to figure out. How do we write that in interval notation? Okay, and so here's how we're going to write this. Instead of saying from negative infinity to positive infinity, we're going to say from 0 to infinity, right? From 0 to infinity. Now, are we including 0? I think we said earlier we're not including 0. So since we're not including 0, we want to use a parentheses here. Parentheses does not include. Right? So in the chat, I wrote parentheses means does not include, but a bracket means include. All right, so I'll show you what I mean by that. Oops. If you had put bracket 0, comma, infinity, this bracket here with the 0 would mean you're including 0. But since we don't want to include 0, we use this regular parentheses. Okay.
I have a question regarding that. I see that there's parentheses around the infinities. How come you don't use a bracket around it even though it goes to infinity?
That is a great question. So because infinity is more like it keeps going forever and ever, we're not actually ever able to get to infinity. And since we can't ever get there, we use the parentheses to say, we're going to get as close as we can get, but we don't actually ever get there.
Okay, thank you.
Of course. All right, last piece to this, the asymptote. And we had written that earlier. There is a horizontal asymptote. And so let's just, whoop, too far. There is a horizontal asymptote at y equals 0. That is a special feature about the exponential function. Okay. All right, so let's go ahead and take a look at setting the stage for what it means to be using these in a word problem. Okay, so this next section, exponential models, if you want to go and read a little bit more in your textbook, actually corresponds to section 4.7 in your textbook. Okay, but we've actually documented quite a bit of this already. So I'm just going to rewrite the equation that we had from above. Okay, so f of x equals, now when we think exponential, right, we do not want to think that y equals mx plus b. What would we be thinking of if we thought y equals mx plus b?
A linear function?
Yeah, a linear function is y equals mx plus b, right? But an exponential, just as quickly as we say y equals mx plus b, I want us to say y equals ab to the x, right? So we know y equals mx plus b is a linear function, but I also want us to embrace that when we have y equals a times b to the x that we're thinking exponential, okay? All right, now we talked about what each of these things means, and we also talked about which one makes it growth and which one makes it decay. I want to focus on one part in particular here, and that is the b value, okay? So this b value that we have right here, right? We said earlier that if we have b is greater than 0, we'll end up with a growth function, okay? And if we end up with b is between 0 and 1, we'll end up with a decay function. We want to be really thoughtful about how we find our b value, okay? As we go through word problems, we're going to find that they will typically tell us this is your initial value. Like they're going to tell us what a equals in most of the word problems, right? They'll be like, this is your initial value, and you're going to put that number right there. And then they'll also tell you like, this is how we're going to count our time, like by the year, by the month, all of that information will be right there. But the hardest part to fill in the number for is going to be the b, okay? And so I want to make a really big announcement about b, all right? That b is not going to equal the percent in the word problem. We're going to see a lot of percents in the word problem. b is not the percent. Okay, b is not the percent. But if b is not the percent, we should know what it is. And it turns out that if we want to find b, we are going to use the percent. Okay, we're going to use the percent to find our b. All right, so the percent tells us about b, it's just not equal to b. All right. In fact, if we have our percent and we plug it into this handy dandy equation, we're going to be able to find our b value. So here's the equation. We're going to do 100 plus or minus the percent, and then we're going to divide it by 100. All right, so if you read through a word problem and you see the percent, if you plug the percent into this formula, then you will get your b value. Okay. I think we've seen this plus minus sign before in like a quadratic formula situation, right? And usually you have to do both when you do quadratic formula. In this one though, we're only choosing one. If you see a growth situation, you're going to add that percent, right? And that should sort of make sense because if we're growing, we want to keep adding more and more. And specifically, we're going to multiply by a number bigger than 1. But if we see a decay situation, then that's when we're going to choose to subtract. Okay, so that is something we need to actively make a decision on. If it is a growth situation, we're going to do 100 plus the percent. But if it's a decay situation, we do 100 minus that percent. Okay. All right, so all of this maybe makes sense if you've seen this before, or maybe sounds like kind of like, I don't even know what we're talking about if we haven't seen this before. So let's actually do a question. And then after we do this question, we'll take a second break because I know this class is very long. And so let's do one example before we take that second break, okay? All right. Anybody out here own a car? I think that folks who have purchased cars or are thinking about purchasing cars sort of fall into two different camps. Like some people, maybe they are very financially stable or they just really want a brand new car. Like I think there's something special about having that brand new car at one point in your life. But other folks are like, I don't want a brand new car. I want just like one that's like an older one, right? It'll save me more money, et cetera, et cetera. Let's take a look at this problem and think about, for you, which one of those might actually be accurate as you sort of move forward in your financial journey, right? So in this scenario, Erin purchased a brand new Toyota Tacoma, $36,000 out the window, right? That's how much she chose to pay for this truck. Now, one thing that if you don't know this about cars is a good thing to know is that most cars do this. Okay. They depreciate. They depreciate. All that is a fancy word to say your car loses value every single moment in time. From the moment you drive that brand new shiny car off the lot, it is already worth less than what you paid for it like 5 minutes ago. And it's not just worth a little bit less, it's actually worth a lot less. So most cars or trucks have a depreciation value. That is something that you can look up before you actually purchase a car. You can say like, how much does this car lose every single year? In other words, what are other people gonna pay for it if I decide I wanna sell this car at some point, okay? And so I looked this up. Turns out that the Toyota Tacoma depreciates by about 17% every year. That means that $36,000 is how much you paid, but in 1 year, you lose 17% of that value, okay? And so our question is gonna be to ultimately find the value of Erin's truck after 7 years, right? 7 is sort of, I mean, if you're gonna have a car, some of us like to get new cars all the time and are able to financially do that. And some of us get that car and we're just gonna drive it into the ground because that is where we see, our money really helping us out. So as we're looking at this problem, a few things pop out at me. I see this 17%. As soon as I see that 17%, and as soon as you see that 17%, I want you to be thinking this. All right, you see that percent, you're thinking, oh, this is an exponential situation. Okay. Now, is this going to be exponential growth or exponential decay? Yeah, this is going to be exponential decay. All right, so in this case, we're looking at exponential decay. And a key word that might tip us off here is that we are depreciating value or we're losing value. So the amount that that car is worth is going to go down as we go with time. Okay, so now part A asks us to write a function. That means we need to find a value for A and we need to find a value for B. All right, so we're going to find a value, the starting value, and then we're going to find that decay constant. Those are our end goals. All right, so I said earlier that A is something that the problem typically gives you right off the bat, right? What is our A value in this case?
36,000.
Exactly, that is our 36,000. Right? So we can even color code that. We can see this is our A value. And so we'll get f of x equals, instead of A, we'll write 36,000. And then we want to think about what our B value is, okay? I'll wait for the screen to catch up a little bit. Da-da. There we go. All right, so we have our A value in here as 36,000. All right, now to find our B, here's what we don't want to do. And I'll write this out just because I don't want us to do this. If you go ahead and put that 17 in there, then you made the mistake that a lot of folks make, right? You're like, oh, this is the percent, it must be our B value. But if we think back to what we wrote on the other screen, the percent is not our B value. In fact, we have to plug it into that other equation to figure out the B value, okay? And so let's actually, instead of writing that 17, let's go ahead and write the equation for B. So we're gonna have 100 plus or minus the percent over 100. But since I already know this is a decay, I'm going to go ahead and only write the minus sign there, right? Again, it's not like the quadratic formula where we do plus minus and we get both. We want to be thoughtful about that choice. Decay means that we're going to choose to subtract here. Then all of that work, we don't want to forget to write the x that is in the exponent. Sometimes that happens. All right, but instead of percent, we're going to go ahead and plug in 17. All right, so I'll erase the words. We're going to put a 17 here. And one of my favorite resources for sort of computations and graphing, I'm going to drop a link in the chat right now. That is the desmos.com. If you are not familiar with Desmos, it is a fabulous free graphing calculator, but it also does like regular calculations as well. Okay. So what I'd like you to do is go ahead and use this Desmos calculator and type in that left-hand column 100 minus 17 divided by 100. All right, so let's just kind of practice using that calculator. And if you just type that in, all right, I think what happens is you end up with something like this, 100 minus 17 over 100. Is that what folks are seeing when they type that in? Now that's not what we mean though, right? We don't want to do 100 minus separately 17 over 100. What do we need to fix here to get the answer that we want to get out? Exactly. Sometimes that is just a simple, let's put in some more parentheses, okay? And so what we want to type in is 100 minus 17 in parentheses divided by 100. And when we do that, I believe we get 0.83. Is that what folks are getting?
Yeah.
Perfect. So we get 0.83 to the x. And so this, my friends, would be our function that models the value of the truck. 3,600 or 36,000 times 0.83 to the x. Okay.
A quick question. Instead of putting it all into the equation, could you do B separately on the side and then plug it in?
Absolutely. That is totally fine. All right, so what can we find with this equation? This equation is going to help us find out the value of her truck after 7 years, okay? So this x in the exponent, I said earlier, that's the time cycle. So everywhere we see an x, we're going to go ahead and put 7, okay? So part B looks like f of x equals 36,000 times 0.83 to the 7th power. And I'll give you a moment to type this all in on Desmos. And let's see if we need any extra parentheses or if we feel like it's good to go. All right. I think in this case, we're okay. Are people getting a number bigger than 10,000 or less than 10,000?
Less than.
Less than, good. Now, a great question that folks always ask is like, how many decimal points, right? Now there's like so many decimal points. We're talking about money, right? And so for our monetary purposes, we go for 2 decimal points because we're looking at dollars and cents, right? And so we should get 9768.98 if we round that last cent. There we go. All right. So yes, we just did some math, but let's think about what this means, right? You walk up to the Toyota dealership, you buy a brand new car, a truck, you pay $36,000 for that truck. And all you do is like drive around town. This is not even like you didn't have any accidents, nobody dinged your car, like nothing. All you did was have this car. Even if you just left it in your driveway for 7 years, your car would be worth less than $10,000. A lot of this value is lost in the first few years. Okay, a lot of this value is lost in the first few years. I'm not telling you how to spend your money. I've done the whole buy a brand new car for myself, done that. I'm glad I was able to do that at some point in my life, but I fully understand and respect why some people would pay for a 2-year-old car or a 3-year-old car, right? You could save a lot of money up front, and as long as the car is in good condition, then maybe you're only losing that smaller percent, right, every single year. Then it's the dollar amount is less every single year. So take that for what it's worth. Think about, you know, as you're looking for cars at some point in your life or any mode of transportation, like what's worth it to you, right? If this is worth it to you, by all means. But if it's not worth it to you, you know, then maybe you need to look at some of those used cars and see what kind of deals you can get over there. All right. All right. So as promised, we're going to take a short break. All right. So I'm going to pause the recording. All right. So our first example was about purchasing a new car, purchasing any sort of car, and thinking about this idea of depreciation, right? And so when you hear that term like, oh, this car holds its value better than other cars, that sort of means that that depreciation number is smaller than for other ones, right? So some cars might like their value might drop like pretty quickly, but other cars maybe it like is a little bit more gradual, right? Okay, so we want to also think about, though, how do things increase in value, right? Not all things about money have to be depressing or like seem unattainable. I think there are actually some really awesome things that we can educate ourselves about in terms of finances. Now, I do want to put it out there. I am not a financial advisor. That is not the purpose of this class, right? But these are just some things to kind of like think about and really for us thinking about like, not just like, how do we do these kinds of problems, but like why they're actually important, right? And so the second example here is about something called an IRA. All right. So if you've ever had a, you know, a job, a full, depends on the job, but some jobs offer retirement accounts. Pretty much all full-time jobs, a lot of them come with a retirement account. And for some of the, some companies will pay money towards your retirement. That is, they might match what you contribute. right? And so that's something like, when you get to that full-time job, like this is your dream job kind of status, and you're thinking, okay, like how do I choose between all of these fabulous offers that I have? Some companies might pay you more, like your salary might be more, which is great. But then other companies, sometimes they have these quote unquote benefits that aren't always visible in your salary. And so some of these benefits include a retirement account. And so what I mean by that is like, some companies might say, oh, if you put $100 into your retirement account, we'll put $100 in there. And then you're going to have 200. So you put in 100 and you get 200 automatically. Not all companies do that, but that could be something that, like, as you're choosing between all of your very awesome job offers that you're all going to have in the future, like, okay, does this company, are they going to take care of me beyond just paycheck to paycheck? All right. And so there are also some places where maybe they don't give you a retirement account. And so what you can do is open up your own retirement account. That's what we call the IRA, or an individual retirement account. Right. So this is something you would do on your own that you don't need a company to do for you. So you can actually open up an IRA right now, even if you don't have a full-time job or a job. You can just go ahead and open up an IRA account for yourself. Now, there is something to think about called this average rate of return. And it means, like, if you think about retirement in like 30, 40 years, well, that sounds kind of sad when we say it that way, but when you think about retirement in the long run, it turns out that on average, your retirement account, including really good years and really bad years, is going to be about 6% per year. Okay. Now, certainly in times where things are a little bit tougher, it could be lower than 6%, but the hope is that in the years where it's going to be good, is going to be higher than 6%. So on average, you'll get about 6%. Now, it turns out that there's a limit to how much money you can put into this account each year. All right. And right now, I think that limit is $6,000 per year. 6,000 is kind of a lot of money, right? But let's think about this problem. Let's say, like, for your first job, right? You get that full-time job and you're like, no, remember I had this math teacher one time who told me that I should put some money into this IRA. So I guess I'm going to do that. And let's say that you put $6,000 in there that year and then you forget about it. You're like, I just, like, all this other stuff came up. I wanted to buy that new car. I wanted to buy a house. I wanted to help my family out. Like, all of this other stuff that your money was going to go towards, you just forgot that you did this. Okay, that's the context of this problem. So let's say that you start with an initial investment of $6,000. Okay. Part A says write a function that models the value of your IRA. And so as soon as we see this 6% per year up here, we want to think f of x equals AB to the x. And we want to think, well, we better know the starting value, and we better find our B value, right? And so I know that someone had suggested earlier, what if you did the work for B on the side? So let's just show what that might look like in terms of your work. But are there any guesses for your A value? What's our little A value here?
6,000.
Yeah, exactly, right? All you're doing is putting $6,000 of your well-earned money into this account. Now, if you want to find the B value, maybe we could write that down here. We could say B is going to equal 100, and then we need a percent, and then we're going to divide that by 100. Are we going to use the plus sign or the minus sign here?
Plus?
Yeah, we're going to use the plus sign because we want to get more money, right? This is a rate of return, meaning every year you get 6% more. And so instead of percent, we're going to put in that 6. Okay, so 100 plus 6 divided by 100. Make sure you have the appropriate parentheses when you put that into Desmos. And what do you get as your B value? Good. All right, can anyone confirm that we get the 1.06?
I got that too.
Perfect,
Yes.
perfect. All right, so let's write this equals 1.06, and then I'll go ahead and put that back into the equation. So if you want to organize your work this way, that is absolutely fine. All right, so our retirement account can be modeled by this equation, 6,000 times 1.06 to the x. All right, so remember, this is your very first year on a job. You're so excited. You put in that $6,000 and then you forget about it. And you retire 30 years later. And as you retire, you're like, oh my gosh, I put in that $6,000 30 years ago. I wonder how much money I have now. Okay. So we're going to take 30. And we're going to put that into our equation everywhere we see an x. So what that might look like, right? So we have the 30, we're going to plug that in everywhere we see the x value. And what that might look like is f of 30. All right, so I'll give the screen a moment to catch up, but we have f of 30. Right. F of 30 really stands for this is how much money you're going to have in 30 years. Okay. And so we're going to have 6,000 times 1.06 to the 30th. All right. Now, I know for the last question, I asked you to just type that into Desmos and it gave us an answer. And I still want us to do that this time. But as a thinking question for ourselves, if we were to do this on a regular calculator, which one would we do first? Would we multiply the 6,000 and the 1.06? Or would we do 1.06 to the 30th? Which one would we do first?
Exponent.
Yeah, we would do the exponent first, right? And so Desmos takes care of that for us, but I don't want us to forget, in case we're ever using a different calculator, we need to do the exponent first and then multiply our 6,000, right? But we can still type this all into Desmos. And how many digits are in front of the decimal place when you type that in? Yeah, in fact, we should get something along the lines of and about 95 cents, right?
That number keeps increasing dramatically because each year you keep putting 6,000, right?
No, all you did was put in $6,000.
Okay, but I mean, if you keep putting 6,000 each year, then it kind of increases quite a bit after a while.
Yeah. So this is only 1 year, right? If you kept adding 6,000 every single year, especially when you're younger, okay? This is the hard part because when you're younger, you typically have less money, right? But if you can put more money into your investment accounts the earlier you in your life, what happens is you have more time for that money to grow. And you don't have to do a lot to make it grow because it's the average rate of return, like whatever the investments are doing, whatever the stock market is doing, it just kind of follows that pattern, right? And so if you make, like you put in 6,000 and when you went to cash out, it was almost $35,000 and you didn't do anything to that. All you did was say, I'm just going to put $6,000 away. Like that's kind of amazing, right? And so think about it. If you put in $6,000 every single year for 10 years, and its rate of return is 6,000 or is 6%, you're going to get a lot more than $35,000, right? You're going to have like hundreds of thousands of dollars just by squirreling away a little bit every year, right? Now, of course, that's not always possible, right? We have a lot of other obligations. Maybe we're going to have our own kids. Maybe we already have our own kids, all that kind of stuff. But it is kind of neat to think about like how much just letting something sit in something that has interest or a rate of return, how much that can actually just make your money grow. All right.
The thing about that is that you can take out the money, like if you need it, you gotta wait 30 years, right?
Yeah, so that's actually a really good point. So some retirement accounts, depending on the ones, allow you to withdraw without penalty, but those are few and far in between. Most accounts, once you put it in there, they will charge you to take it back out. So if all you have is $6,000, I would not recommend putting it all in an IRA, because like, what if you need a security deposit for an apartment? Or what if, you know, you need to do some maintenance on your car? Like, it should not be your only $6,000 that you put in there. Like, it's not like a savings account, but if you are able to put in even like $1,000, a little bit a year, $50 a month, whatever you have, it does tend to pay off, especially if you do that when you're a little bit younger. You know, we don't always think about retirement when we're younger, but it is something that is, you know, important. All right. So we've talked about cars, we've talked about investment accounts. We're going to talk about a few other sort of common applications of exponential and exponential growth and decay. All right. So along the more classic lines that you might see in a textbook, we actually also use exponential functions to model population growth, right? Population growth and decay. And I don't know how many of you are out there interested in like environmental science, but thinking about, you know, animals, endangered species lists, all that kind of stuff. A lot of that population modeling is done based on an exponential model. So manatees, I don't know if you've ever seen a manatee, but they're kind of like bigger than seals, I would say. Ocean animals, actually maybe lake, I don't know. But anyway, they were recently removed from the endangered species list, which is pretty cool. So let's say that there are currently 13,000 manatees and the population is growing by 1.5% each year. Write a function that models the population of the manatees. And so as soon as we see that 1.5%, we're automatically thinking f of x equals a times b to the x, right? We're not thinking y equals mx plus b, but we're thinking y equals ab to the x. And so while we're waiting for my screen to refresh, oh, there we go. Let's go ahead and in the privacy of your learning environment, if you could go ahead and find a value for A and find a value for B, and either send that to me directly in the chat, or you can post it in the whole group chat, up to you. But let's find a value for A and a value for B. All right. Good, good. It looks like there's a lot of agreement here on what we have. So since the population here is growing, right, in a good way, that population is growing, we want to make sure that our B value is bigger than 1. And it looks like everyone who has sent me a message has indeed plugged in the right values. So we should get f of x equals the initial amount, right, which is our 13,000. We're going to do 100 plus 1.5 over 100. We're going to raise that to the x power. And if we clean this all up, we'll get an equation that says f of x equals 13,000 times 1.015 to the x. All right. Perfect. Now, tell me about the procedure for part B. What are you going to do in order to answer part B?
We're gonna plug in 5 in the exponent x.
Perfect. So we could say that f of 5 equals 13,000, 1.015 to the 5th power. And remember, even though when we type this into Desmos, it does this for us automatically, we want to know, we would do the exponent first, and then we would multiply in that 13,000. And I believe that gets us to about 14,004. And if we were to write down the first few decimals, we would get like 0.6 something, 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 right? Now, when we were looking at money, we knew we needed to round to 2 decimal places because it's money and we're looking at dollars and cents. What might be a good number to round to here in this context?
You would have to round to a whole number, so you could either round up or down. In my case, I would round down since you can't really have a partial manity. And so you would round to 14,004.
Yeah, I think that's a pretty good explanation right there. That, you know, if you want to split some hairs, you could say, well, we have 14,004 and maybe like one of the manatees is pregnant, you know, maybe about like, I actually don't know how long they're pregnant for, but like for like 0.7 months along the way, you know, but in general, when we're looking at population, we tend to round down because we're looking for whole numbers or things that actually are possible, okay? All right, so example 3, I think very similar to example 1 and 2, but also like a common kind of way to look at exponential functions. And then the last example we have here underneath this category of sort of word problems is one of the more common decay situations. Okay. And so this is a phrase that, especially for those of us who are STEM majors, you're looking like bio or chem or physics, this phrase, half-life, is going to come up quite a bit, right? So I want it to be something that we're familiar with. It's not like a phrase that's like, ooh, what does that mean? Okay. All right. So we have mercury 197. All right. So Hg, mercury 197. And I'm actually going to go ahead and cross out that 197. All right. That 197 refers to an isotope of mercury, which is not really of concern to us because we're not really looking at isotopes in our class. But it's sort of included in the name of the thing that we're looking at. Okay. And so I just cross out that number because I don't want us to sort of panic plug in numbers into our equations, because that number, it's actually there as a distractor. Like we don't need to use that number in our equation. Okay. But it turns out that when we use this in a kidney scan, it has a half-life of 64.128 hours. And all that means is that every 64.128 hours, we have 50%. Oops. We lose 50% of the amount. Give the computer screen a moment to catch up, but every 64.128 hours, we lose 50% of the amount that we had, okay? So let's say that we start off with, in this case, if we read the rest of the question, it says that we have a 12 milligram sample, right? So at the end of one half-life, how many milligrams do we have of this mercury isotope? And if we start off with 12 milligrams, at the end of one half-life, how much do we have left? Okay, that's a good guess. What's your reasoning for 1.5? No, I wasn't asking for B. I was asking for like, if we have 12 milligrams to start, how much will we have after one half-life? So in other words, after 64.128 hours, how much do we have left? And Matthew, you are correct. There would be 6 milligrams. Okay, so we start with 12, and then after one half-life, we're going to have half of that. All right, how much would we have after another half-life?
3.
3, good. So after a second half-life, would have 3 milligrams. Okay, how about after a third half-life?
1.5.
Yeah, we would have 1.5. Okay, and so using that idea, right, we're going to think about how we write this exponential decay function. All right, so we're losing value, right? We start with 12, then we have 6, then we have 3, then we have 1.5. And so we are decaying, or we're losing value, right? That means that when we find our B, that we better use the subtraction and not the addition, right? So if we write this out, f of x equals ab to the x. I'll give the computer screen a moment to catch up. And we start plugging in our numbers. I think we're going to find that we have a 12 in for our A, right? That's our starting amount. And in for B, I would write 100 minus, because we're losing value, 50 all over 100 raised to the x power, right? When we do 100 minus 50 over 100, what do we get?
50%. I mean, like 0.5.
Yeah, we get 0.5, right? So if you don't want to write that every time, one shortcut that's kind of nice is that when you see a half-life, you know that B equals 0.5. All right, when you see a half-life, you know that B equals 0.5. And that's just because you're losing 50% every time. And so you always end up with 0.5. All right. The other thing that I want us to think about here is this exponent x. All right. I'm going to include something else to this exponent. In fact, I'm going to make this not x, but I'm going to make it x over 64.128. Okay. We're going to work through part B, and then I'll explain why we're dividing that. All right, so let's work through part B, and then let's explain why we divided that the way we did. All right, to find the amount remaining after 72 hours, how many half-lives is that, by the way?
72 hours would be one half-life, but there is still some left over, which is, I'm assuming, why you had the divided by 64.128.
Yeah, exactly. 72, it's definitely more than one half-life, right? Because one half-life is 64 hours, but it's not two. It's not a full two half-lives, right? And so we'll find f of 72. We'll go ahead and do 12 times 0.5 to the 72 over 64.128. And I'll give you a moment to put that into Desmos. You want to make sure that you got all the parentheses and division symbols, but confirm my answer. I got 5.510 milligrams. All right. So folks, we actually have Yizan in the space right now. And so I know it's kind of sort of important for us to, know who everybody else is in this space, but also in particular, because he is your peer mentor, making sure that you know if you're going to go to a tutoring session, who you're going to go see. And so I'll pause the video for a second. So once we have the equation, we can plug it into Desmos. That's not the problem. But I really appreciate you following up on but why in the world are we dividing by that 64.128? And so here's our reason for that. Okay. We want everything in the pink to be a time cycle. And what we mean by that is we're not counting in hours here, but we want to count in half-lives. So we want to count how many half-lives. Okay. And so when we think back to our questions earlier where I said, okay, well, if you have one half-life, then you would end up with 6 milligrams, 2 half-lives, you would have 3 milligrams, 3 half-lives, you would have 1.5 milligrams. We got that number by really saying everything in the exponent is going to be is counting half-lives. And so we need to divide by the hours. So it'll tell us how many half-lives we have, if that makes sense. Yeah.
Thank you.
You're welcome. All right, so we're going to finish off with three questions here, okay? And if we don't get to all of them right now, that's okay, but I'd like to get as far as we can get. And so we're actually going to start with example 6, all right? So we're going to skip example 5 for right now. We're going to move on to example 6. Okay, and so these are a little bit less application based, right? It's literally just like a very classic question that we might see in the beginning of a textbook. Find an exponential function that passes through these points, -2, 6 and 2, 1. All right. Now, one of the things that I like to do before I get started is actually imagine in my head whether it's going to be growth or decay. All right. And so here's how I imagine this. I actually do just kind of a quick sketch. there we go. Okay. I do a quick sketch to see where those points are and whether I'm going to get a growth or decay situation. No, I don't like that. So if I plot the point -2, 6, that's going to be like somewhere up here. And then if I plot the point 2, 1, that's going to be somewhere down here. So are we thinking exponential growth or exponential decay?
Decay.
Exactly. We can almost imagine there might be something kind of like this happening, right? And so since we have a decay, what does that mean about our B value?
B will be between 0 and 1.
Perfect. We're going to have B sandwiched between 0 and 1, right? Perfect, exactly. And so if we're going to end up at the end, if we end up with a number bigger than 1, we know we made a mistake somewhere, okay? So it's nice to do a little bit of sort of what I call pre-thinking, like planning out what we're going to do and what kind of answers we should expect. But we can break this down into a few steps, okay? And so what we're going to do right now is our step 1, okay? We are going to go ahead and write the 2 coordinate points. Right, so the 2 points that we are going to use to find whether this, find the equation are actually given to us right here, right? We have -2, 6 and 2, 1. We won't always have that information so clear, which is why I make it like an actual step. Okay. So a good first step would be to write out the 2 coordinate points. Then what we're going to do is this. We're going to substitute both points into f of x equals ab to the x. Right. And here's what I mean by that. We're going to say for the first one, what would I put in place of f of x? I'm looking at the coordinate -2, 6. What do I put in for f of x?
-2 and 2, both of the both of the x's.
Okay, maybe I phrased this not very well. I'm going to replace the word both with the word each. We're going to substitute each point into f of x equals ab to the x. Yes, I think I asked that not well. In other words, f of x is like a y value, right? And so if I have the point -2, 6, everywhere I see f of x, I can put a 6. So I would get 6 equals ab to the -2. Does that make sense to folks, where we're getting that from?
This is just the y, just the y intercept.
Yeah, so we have y goes here and our x value goes in for the x. All right, so that's for one of the points. Now we're going to do the same thing with the other point, okay? So what would I write for the second point being plugged into that equation?
One equals AB squared.
Good. 1 is going to be the yellow one, right? And 2 is going to be the x value. So 1 equals AB to the power of 2. Right. All right. Now, what we're going to do, we're going to take each equation. So in each equation, we're going to isolate A. Then set the two equations equal. Right, now let's make sure we understand what that means, that I'm using language that's clear for all of us. So in each equation, excuse me, we're going to isolate A, and then we're going to set those two equal to each other. And so if I were to take a look at this first equation here, and I wanted to get A all by itself, I would have to divide away this B to the negative 2. And so that would look something like this. A equals 6 over B to the negative 2. Okay. What does that look like if I isolate A in the second equation?
A over B to the 2.
So I want to get A all by itself here.
Oh yeah, my bad. A equals 1 over B squared.
Good. Yeah, we're going to divide away the B squared, right? So we'll get A equals 1 over B squared. Okay. So we've isolated A in each equation. And what I mean when I say set the two equations equal to each other is 6 over B to the negative 2 is equal to A, but so is 1 over B squared. They're both equal to A. What that means is that they must be equal to each other. In other words, 6 over B to the negative 2 must equal 1 over B squared. We're going to be able to find a value for B. That'll be headed in the right direction, because ultimately we want to find a number for A and a number for B. Okay. So I see a fraction equals a fraction. Okay. When I see a fraction equals a fraction, and cross multiply. Okay. In other words, we can do 6 times B squared, right? That cross, that part of the cross, equals 1 times B to the negative 2.
I have a quick question. So
Absolutely.
I'm noticing that one of the fractions is b to the negative 2. Since
Mhm.
it's to the power of negative 2, can't you flip the b to the other side and have it be 6b squared?
Yes, you can.
Okay.
All right. I'll show you why we're not doing that. And it's mostly just to highlight some exponential strategies that maybe we knew a long time ago, but sometimes it's good to refresh a little bit. Okay. So if we cross multiply here, we'll get 6b squared equals 1b to the negative 2. All right. Now, if I want to get all the b's on the same side, all right, but keep the exponent positive, here's what I'm going to do. I'm going to take this b to the negative 2. I'm going to divide it over to the left-hand side. And at the same time, I'm going to take this 6 and I'm going to divide it over to the right-hand side. And we're going to end up with b squared over b to the negative 2 equals 1/6. What's another way of writing b squared over b to the negative 2? In other words, what is that exponential rule about how we can combine exponents? Because sometimes we can and sometimes we can't. And then there's like, sometimes we add, sometimes we multiply, sometimes we subtract. Like, what do we do here?
In that case, would we subtract the exponents?
We would, exactly. And the key thing here is that division symbol, right? The division means that when we look at our exponents, we're actually going to subtract them, right? And so we're going to have b to the, let's see, what is 2 minus negative 2? That's going to give us b to the 4th over equals 1/6. All right, my friends, how do I get rid of that power of 4?
You can do like the root thing.
Yeah. In particular, what root should we do?
A quad root?
Yeah, like I think we actually call it a 4th root. I think there's like the cube root, and then after that, we just give it like the number. But yeah, we could write it like this: b equals the 4th root of 1/6, right? That is one way we can write it. Now, if you can't find this button on Desmos, right? If you can't find this button on Desmos, how else could we evaluate this? Like, how could we use Desmos to help us find this value? Right? Because there's nothing mathematically wrong with what we wrote here, but I bet we're going to have a hard time finding it on some calculators. And so another way that we could actually write this is like this: 1/6 to the power of 1/4. That I bet you can find on Desmos. Okay, so I'll give you a moment to go ahead and type that into Desmos, see what you get. And let's go to 3 decimal places here. Okay, let's go to 3 decimal places.
Professor Wu, I had a quick question on one of the steps in that last equation.
For sure.
Here, I'll turn my camera back on. So I'm not understanding how you can divide b to the negative 2 power on both sides of the equation and also flip the 6 over to the other side of the equation. I'm trying to understand how that's done, because that helps me sort of understand the equations and the patterns and the structure, but that step is really confusing the hell out of me. I don't know how you did that.
Okay.
You kind of just said you did it, but maybe I missed how you did that.
Okay, so let's do it one step at a time then. So I'm going to keep, the only thing I'm going to do is divide this b to the negative 2. Okay, so I would get 6 times b squared over b to the negative 2 equals 1. Now I want to divide the 6 to the other side. That's how I get the 1/6 on the right-hand side. Does that make a little bit more sense? Oh, I think you might be muted, so I missed what you said.
I'm sorry. Yeah,
No, you're
I
fine,
was.
you're fine.
That makes total sense because I'm probably not in the alone when this. So I wrote 6b squared divided by b to the negative 2 power, and you got to leave 6 out of its own
Oh,
separate,
you
and then.
you can write it that way too.
Well, no, but see, if I'll confuse the heck out of myself if I write it like that, because I usually don't put the multiply sign. I just write 6b squared, right?
Ah,
So if I don't separate that sort of however way you can separate it with the multiply dot or with parentheses. Yeah, no, I was my bad. So thank you for clarifying that. Appreciate it,
of
Professor.
course, of course. All right, so now if you were to type this 1/6 to the 1/4 power into Desmos, I think you get about 0.639, right? Yeah, exactly, Dallas. And I would say of all of the steps here, this last one is honestly the least important to me. I love where everyone's questions were about like, but how do we get from one step to the other? That's really where we need to invest our emotional energies here and understanding, okay? All right, so to recap, we wrote our 2 coordinates, we substituted each point into the equation, then we isolated A, and all of this gave us a way to find B. Our 4th step is going to be to solve for A, right? Because in order to write this function, we need an A value and a B value. And so we have a few choices. In fact, we have 2 choices. We can either use the first equation, plug in our B value and find A, or we can use the second equation, right? And I would argue that there are even more efficient equations that we could use that are on this page right now. In fact, if we sort of bring our eyeballs to this equation, we already solved for A, right? A equals 1/b squared. This equation might be the easiest one to help us find A. Now, let's say you chose to use the first one, nothing wrong with that, right? You can use the first one. I think the second one is a little easier because there's no negative exponent. That would be the only reason I choose the second one, okay? And so when we find that, we get A equals 1/0.639 squared, and that gives us about 2.449, I believe. Okay. Our last step here, we're going to write the function with A and B values, all right? So we don't want to just like find the values and be like, I found the values, we're all good. We actually want to finish the problem and write our answer in a way that makes sense for what we're being asked, okay? And so we would write f of x equals, instead of A, I'm going to write 2.449. Instead of B, I'm going to write 0.639 to the x. Once I've finished that 5th step, that is our final answer. Because if we show all of this on one page, we found an equation, an exponential equation that passes through these 2 points. Okay. We're not going to go over example 5. But what I will do is this. I'm going to write the answer for number 5. And if you felt like you could really practice this process again, like the one we just did for number 6, use those 5 steps I bet you'll be able to get the answer for number 5, okay? So I'm just going to write the answer here. F of x should equal 80 times 1.145 to the x. Okay. F of x equals 80 times 1.145 to the x. Now, if you work through this problem and you get stuck, come to office hours on Wednesday. We will walk through it step by step. I am more than happy to do that with you. All right, so that is a great, if you're like, I don't really know what questions to ask, you can bring this question, say, can we go over it together? And we can walk through it step by step, okay? All right, so I'm gonna stop the recording here.